Hello, and welcome back to yet another session in Geology 1 Processes and Products. Today we continue our investigation of the hydrologic cycle, looking at the third greatest reservoir of water in the hydrologic cycle. Today we're discussing groundwater. Let's get started. So, groundwater simply refers to that water which is stored in underground rocks. It is the third largest reservoir of water, but most importantly for humans, it's the most important source of fresh water, our drinking water source. It is a geologic agent. A geologic agent is anything that erodes, transports, and deposits. If we take a look at the hydrologic cycle, we can see that most of the water is stored in the ocean. Our second largest reservoir would be glaciers, but we're talking today about the water that is contained in rocks, in the pore space, and rocks in the subsurface. Now, in order to have groundwater, in order to be able to store water in the ground, we need two important factors to be present. Those are porosity and permeability. Porosity refers to the percentage of the material which is pore space. One of the best analogies for porosity involves different size balls. Take a look at the room in which you're sitting and imagine that it's completely stuffed with volleyballs. That space between the volleyballs would be the space where water could be stored. Now, think of your room as being stuffed with tennis balls. You've decreased the space available in your room to store water because the space between the tennis balls is going to be less than the space between the volleyballs. There's still a lot of porosity left, however, even if your room is stuffed with tennis balls. What if we take a room of volleyballs and then add the tennis balls between the volleyballs? Even less porosity would result. So if we had one grain size, we would have greater porosity in the rock. The porosity will depend on the size, the shape, and the arrangement of the grains. And again, one grain size, greater porosity. Usually a well-sorted sedimentary rock with rounded particles has high porosity, whereas in this diagram you see a poorly sorted one. We have different size grains. It won't have as great a porosity. In limestone, porosity can be increased by solution, whereas with metamorphic and igneous rocks, porosity can result through fracturing as opposed to dissolution. Check out some of the porosity values for different minerals. Which material would you suspect would serve as a barrier? Which sedimentary rock would be a good cap rock to prevent water or even petroleum from migrating upward? If you said shale, you have a good choice. The percentage of the porosity in shale is much smaller than that of sandstone. Now remember, in order to have groundwater available in the subsurface, we need not only porosity, we also need permeability, which is the capacity to transmit fluids. An aquifer is a rock body that transmits fluids, but an aquiclude prevents fluid movement. In our previous example, when we looked at the shale would be an aquiclude, but an aquifer would be the sandstone. When we look at the subsurface, we have two different zones. We have a zone of aeration and a zone of saturation. The water table will be the surface that separates these two zones. The zone of aeration is nearest the surface. In the zone of aeration, surface water can move through the zone by infiltration. So after a rain event, the water seeps into the ground. In the zone of aeration, notice that the pores, the space between the grains, contains not only water but also air. Moving down farther past the water table, we get the zone of saturation. In this diagram, you can see that the pores are completely filled with water. Well, how does that look in a cross section? Here we go. Notice that the zone of aeration is closest to the surface. After a rain event, water will seep into the ground or infiltrate into the ground. The zone of aeration will contain both water and air in the pore space. And after you move past the water table, that's the blue line on this diagram, you see that we move into the saturated zone, the zone of saturation, in which all of the space between the grains is filled with water. So that surface that separates the zone of aeration from the zone of saturation is called the water table. A water table generally follows the topography or the lay of the land. So where you would have a valley, the water table would be lower. The water table is generally higher in mountainous areas. The capillary fringe is that area where the water moves up from the zone of saturation by water tension. Here's an example. You can see the capillary fringe is that area where that red dye, water, has moved up into that porous paper. Another diagram, you can see that we have water moving through the zone of aeration, and the zone of aeration contains pores that have water as well as air. Then we move down into the water table into the zone of saturation. In the zone of saturation, there is only water in the pore space. But notice above the water table, we do have an area where the water from the zone of saturation will rise through capillary action, and that's called the capillary fringe. Now, the water table level can change. It's not static. It will change depending upon the amount of rainfall as well as the amount of water, groundwater, which is withdrawn from the zone of saturation. Sometimes we can have a perched water table. This is a lens of groundwater that is found above a local aquiclude. Remember, an aquiclude is a body of rock that does not allow water movement. It's not permeable. So check out this diagram. Note that we have groundwater in the zone of saturation in the blue area toward the bottom. Notice the zone of aeration, which is above the water table in the capillary fringe, and this is where rainwater will infiltrate through the subsurface, the zone of aeration, down to the water table into the zone of saturation. However, look on the right side of that diagram. We have a local aquiclude. Here is a shale body that prevents the water from infiltrating down completely through that zone of aeration. So water would accumulate above that aquiclude, and we would have a perched water table in that area. Groundwater moves from areas of high pressure to areas of low pressure. The controls on water movement are gravity as well as the pressure of the fluid. Generally, we can say that groundwater moves in broad, looping curves in the subsurface. The movement can be fast or slow, but in general, we're only talking about a few centimeters per day as an average. In this diagram, you can see a stream in the middle at the bottom of the hills. We also have a local aquiclude on the left-hand side of the diagram. But as water moves through the subsurface, through the zone of aeration, into the zone of saturation, it infiltrates down. Once we get to the zone of saturation, however, the movement of groundwater will be in these broad, looping curves. A recharge zone is where water is added to the zone of saturation or to groundwater. So this is where the water is added to our groundwater source. If you're driving along the highway, you may see a sign such as this. This one notes that it is an environmentally sensitive area. It's a recharge zone. So this is where the water from the surface infiltrates down into our zone of saturation. So the water is added to the zone of saturation, or to groundwater, at the recharge zone. The opposite of that, of course, would be a discharge zone, where water is released to the surface. Now, where does this occur? This occurs when the water table intersects the surface, or when we drill into the subsurface, into that zone of saturation, and pump groundwater out. A spring is where the groundwater flows naturally or seeps out of the ground. Let's take a look at that. Here's a diagram. You can see we have some permeable sandstone beds. Those would be aquifers. And there are some impermeable shale beds which serve as aquicludes. And the groundwater is accumulating on top of those shale beds. Wherever that groundwater will intersect the topography, the surface, we can get some natural springs. For example, here and here from that local aquiclude up at the top. And when you look at the lower aquiclude, we have some more springs that result from the intersection of the groundwater with the surface. Now, streams can be either influent or effluent. Notice the relationship between groundwater and a river system. Okay, this can be different. In the top diagram, the river is actually recharging the groundwater. The stream is influent. It is losing water. The water from the river is now recharging the groundwater. In the bottom diagram, however, we have something totally different. We have an effluent or gaining stream where the groundwater is recharging or feeding the river. We can also retrieve groundwater by digging or drilling into the zone of saturation. We can't retrieve water in the zone of aeration because not only do we have water in that pore space, but we have water and air. So we need to be in the zone of saturation. So here we have a water table, and that's the dotted line separating the blue from the brown. Again, the zone of aeration is above the water table, whereas the zone of aeration is above the water table, whereas the zone of saturation is below the water table. This well has been drilled into the zone of saturation, and water can be pumped out. Now, if we pump out water too quickly, we can end up with a cone of depression, and this is where the groundwater is lowered in the vicinity, is removed faster in the vicinity of the well. So the water table is actually lowered in that area around the well. So here we have two earlier wells that are no longer producing. Originally they were, because you can see the dotted line of the former water table. However, the water was pumped out faster than it could be replenished, so now we have cones of depression around those wells. The newer well in the middle has drilled deeper into the groundwater area, but you can see how the water table has been depressed in the area through pumping faster than the water can be replenished. The difference between the water table and that cone of depression, this area, is called the drawdown. You can see that a water table can fluctuate with the seasons. We can have dry seasons as well as rainy seasons. So the shallow well on the left would operate when the zone of saturation, the water table, is higher than in a dry season. However, that deeper well will operate all season long as we don't draw down faster than it can be replenished. Notice we do have cones of depression that have formed around both of those wells. An artesian system occurs when the pressure causes the water to flow upward without being pumped. You may notice at the store that you can buy drinking water that is artesian spring water, and this means that the water flows naturally. It doesn't have to be pumped from wells. A potentiometric surface is the level to which the water will rise in the wells, so if the potentiometric surface is above the ground surface, then we have an artesian system. Let me show you how this works. A simple analogy. Here we have a fellow who is pouring water into a funnel that is connected to a leaky hose. Notice the water is rising up from the hole in the hose to about a foot. That would be the potentiometric surface. This is also the way that your city water system works. Notice that on the left-hand side we pump water into the storage tank, and the pressure surface, the level to which the water will rise, decreases from the tank outward. However, when we turn on the tap, there is enough pressure that the water will flow out of our faucet. This occurs in a natural environment as well. The dashed blue line below the surface, below the green, shows the potentiometric surface. And over here on the left, you can see that the surface of the ground is below that blue line. So that is a flowing artesian well. Look over on the right-hand side of the diagram. A well has been drilled. However, the surface of the ground is above that dotted blue line, or the potentiometric surface, and therefore that is a non-flowing artesian well. Here is an artesian well in South Dakota in the early 1900s. Okay, let's shift gears a little bit and talk about groundwater as a geologic agent. Remember, geologic agents erode, transport, and deposit, and groundwater is no exception. As a geologic agent, groundwater erodes because it dissolves and creates pore spaces in rocks in the subsurface. It can form caves, sinkholes, and karst topography. This is a famous sinkhole that formed in 1981 in Winter Park, Florida. Sinkholes form when the rock below the surface is dissolved, and depressions can be created in the earth as the rock that is dissolved and removed, the surface will collapse on top of it. So this sinkhole formed when the overlying rock collapsed into the dissolved cavern below. This is a sinkhole in Montana. It's now filled with water as a small lake. With extensive erosion of limestone, we can get karst topography. Caves, sinkholes, underground rivers, and solution valleys are all indicative of karst topography. Advanced dissolution of the underlying soluble rocks is the cause of karst. Regions in the U.S., such as Kentucky, Tennessee, Missouri, and Florida, display karst topography. It's characterized by caves, springs, sinkholes, solution valleys. And solution valleys form where sinkholes merge. Here are springs. There is a sinkhole. And this is a solution valley, which has resulted when the sinkholes have merged. There's also a disappearing stream, where a stream that's running along the surface suddenly disappears in the underground. That's also a characteristic of karst topography. And this is what happens with very advanced karst, or karst on steroids. This is in China. It's the stone forest a very high relief karst landscape. This is a more subdued karst topography in Bowling Green, Kentucky. What features can you see that would identify this as karst? It's a rolling topography. There are some sinkhole lakes, sinkholes, and solution valleys. There we have a sinkhole lake. That's a sinkhole. And here's a solution valley. Now, caves form when groundwater dissolves in enlarged fractures in carbonate rocks. So this is another way that groundwater can erode and act as a geologic agent. Here we have a stream. The water table is indicated by that dashed black line, and as the water infiltrates into the subsurface, it's dissolving different cavities in that rock. The underlying rock here is limestone. You can identify this as a karst topography from the surface by the sinkholes. Now, look what happens here. Our stream has downcut. This can happen either through lift of the land, or it can happen downcutting of the rivers as the sea level drops. But regardless, look where the water table is now. And the water table is much lower, and these different solution cavities in the limestone are now exposed to the air. Here is our cave. Some different cave features include soda straws, very narrow, thin stalactites that hang from the ceiling, stalagmites that form from the ground, columns where the stalactites and stalagmites join. We can also see drip curtains and travertine terraces. So again, stalactites form from the ceiling and soda straws. Stalagmites form from the floor of the cave upward and build as calcium carbonate is deposited. Columns, where we join a stalactite and a stalagmite. Drip curtains. Travertine terraces. And here's a photograph of Buchan Cave in Victoria, Australia. If you've ever visited a cave, you've probably heard that the difference between stalactites and stalagmites is that stalactites hold tight to the ceiling, while stalagmites push with all their might from the floor. A geologic agent not only erodes, but it also transports and deposits. The way that groundwater transports is through solution. It doesn't roll sediments along the ground like a river would. It doesn't have a bed load, but it will transport in solution. Groundwater also deposits. It precipitates mineral in the pore spaces of the rocks, and it is one of the main agents of lithification. Lithification is the process by which sedimentary rocks are created through compaction and cementation. Here is a petrified log in the Painted Forest in Arizona. The silica that was precipitated from groundwater filled the cells in the wood and resulted in excellent preservation or fossilization. Now, how do humans interact with groundwater? As we mentioned previously, if we pump out water faster than it is replenished, we can create cones of depression around a well, and we can also lower the water table. We can also see a problem with saltwater incursion, and this happens in coastal areas near bodies of salt water. Note in this diagram, the original water level is the dashed black line up at the top, and the windmill has been pumping water. Now we have an overdraft, a drawdown, to the present water level toward the bottom of the screen. The blue areas in this map show declines greater than 15 meters in groundwater. Only along the Platte River do you see rises above 3 meters. So humans do have an effect on groundwater. It has been mentioned that groundwater is a mineral, and we mine the mineral. So it is a resource that can be renewable, but if we mine it or withdraw it faster than it is replenished, we have a very limited amount. What happens with saltwater incursion is that the fresh water forms a lens over saltwater in areas near seas and oceans. This is because the fresh water is less dense. It doesn't have those extra salts dissolved in it. This is the same density principle that makes a regular can of soda sink like a stone in water, but not the diet soda can. So when the fresh water is pumped, the lower lying salt water can come up through a cone of ascension as the cone of depression develops. And you see that's what's occurring in that second diagram. Sometimes by pumping fresh water back into the system through recharge wells, you can lower that saltwater-freshwater interface, and that is the bottom diagram on your screen. Humans, by withdrawing groundwater extensively and faster than it can be replenished, can also cause subsidence. And this occurs as the sediments are desiccated and compacted by withdrawing that water. The land level is lowered. Sometimes in extreme situations, we can see a lowering of about 9 meters. Here we have the San Joaquin Valley. In about 52 years, 9 meters of subsidence. Check out the level in 1925. That's where the surface was. The famous Leaning Tower of Pisa. This resulted from uneven subsidence when they were building it. The renovations actually ensured that this original lean was maintained. So the building became famous because of the lean, because of the uneven subsidence, and when they renovated the building, they wanted to make sure they maintained that natural lean. Nope, this photo isn't crooked. Excessive groundwater withdrawal in Mexico City resulted in a modern uneven settling of buildings. This is Our Lady of Guadalupe Church, settled more than 3 feet, more than 1 meter on its right side when groundwater was pumped out excessively. A more historic version, this is petroleum withdrawal in Long Beach, California. This was taken during the early years, the early 1900s, and up to 9 meters of subsidence was recorded here as well as the San Joaquin Valley. Those white posts in the black and white photograph are well stems. Those were actually at the surface when they were put in. In addition to lowering of our water table, saltwater incursion along coastal areas, and subsidence, we also can interact with our groundwater through pollution. Very common saying is, you dump it, you drink it. That motor oil you dump in your backyard slowly will infiltrate through the zone of aeration into the groundwater in the zone of saturation, and eventually it does reach your groundwater. Septic tanks, solid waste facilities, and underground storage tanks are all ways in which we can pollute the groundwater if we're not careful. So, the way a septic system works, the sewage is released in the zone of aeration, and bacterial action will degrade the waste and filter out those impurities before the contaminated waste would reach the water table. That's how it works in theory. However, we can have water with pollutants entering into the zone of saturation. The contaminated water can travel and infiltrate down from a landfill that's unlined. Once it's into the zone of saturation, it's picked up by groundwater. Notice at point 3, there is a well that can pick up those contaminants in the groundwater. Other sources of pollution, pesticides, agricultural use. animal waste in the lower left-hand corner, domestic trash, improper disposal of trash, and industrial pollution as well. Love Canal is a very famous and tragic example of improper disposal of waste materials. And not all chemicals will travel down into the groundwater. Some chemicals actually are lighter in density than water. Gasoline, for example, will form a lens on top of the groundwater. Toxic chemicals that are denser than water will travel down to the impermeable rock below the zone of saturation. So depending on the chemical and its density, it can affect various levels of the zone of saturation. Okay, another shift of gears. Let's talk a little bit about hydrothermal activity. This involves groundwater, and the magma or cooling igneous rocks in the subsurface provide the heat. Geysers will erupt when the water comes to its boiling point in the subsurface, and fumaroles will vent steam at the surface. This, of course, can be harnessed for geothermal energy. This is a hot spring in Thumb Geyser Basin, Yellowstone. A hot spring has water temperatures higher than 37 degrees Celsius, or the temperature of the human body. Notice the steam. This is a mud pot. A mud pot is a hot spring where the chemically weathered rocks yield clays that will bubble. This one is in Lassen Volcanic National Park. And here we have a diagram showing how a geyser works. Geysers erupt when the groundwater percolates down and then is heated by hot igneous rock below. The water is heated above its boiling point, or when a pressure drop causes the water to steam. The steam's increase in volume will then push the water out of the ground, resulting in a geyser. And of course, one of the more famous geysers, Old Faithful in Yellowstone National Park. Now, check out this map. Notice the location of geysers in the United States of America. Can you tie this to plate tectonics? Where do we see the more active geysers in the United States? Note the mountainous regions. And of course, in mountainous regions, we have subduction occurring at the plate boundary along the western side of the continent. So we would expect to have hot magma from a subsiding plate, as the plate is as the plate is subducted below the overriding continental plate, we'll get partial melting, and then that magma will rise. So we would have a magma source, hot, cooling, igneous rocks along the western U.S. And of course the Appalachians mark the remnant of a much older mountainous system. Well, that concludes the lecture on groundwater. If you have any questions, please feel free to post them on your discussion board or email your instructor. Thank you so much for joining me, and have a great day.